Hi guys, so here we're talking about half-life calculations in nuclear chemistry. You'll need your notes, your calculator, as well as table N, so make sure you have that out. We'll talk about the half-life concept, how to use table N, and then go through some calculations. So half-life is pretty much how long it takes for half of a sample to decay. So say, for example, I've got 100 cookies. It takes, about a minute for me to eat like 50 of them, let's just pretend. So it should take another minute for me to eat another half of them and another minute for the other half. Alright, so here we're starting out with, on the y-axis we have the amount remaining in percent, and in the x-axis we have the time in years. So here we have, it's out of 100, so make it easy. We're going to look at how much is remaining after half of that. So half of 100 is going to be 50. So 50 is kind of like the baseline there. So it takes 5,730 years to go from 100 to 50. Well, let's go through, and half of 50 should be 25. So let's look at that. It takes 11,460 to go from 50 to 25. If you calculate that out, that's another 5,730 years. So 5,730 is right that distance right there. Half of 25 is 12.5. So the time it takes to go from here to here is another 5,730. So keep going. Half of 12.5 is 6.25, which is right there. So again, it takes another 5,730 years for that to occur. So we keep doing this until it gets to a really teeny tiny minuscule amount. What table N tells us here is pretty much what the half-life is for certain radioisotopes. So we've used table N before by looking at the decay mode. Now we're going to look at the half-life itself in that column. The D stands for days, the Y is years, the MS is milliseconds, we have the S is seconds, minutes, pretty much going through those. So each nuclide or each radioactive isotope has its own unique half-life, or how long it takes for half of it to decay. So some of them are really quick. So for example, francium-220 takes 27.4 seconds for half it to decay. So if you have 50 grams, it takes 27.4 seconds to go to 25 grams. Another 27.4 seconds to get to 12.5, and so on and so forth. Some are really long. So we have uranium-233. It takes 1.592 times 10 to the 5th years. Over here we have uranium-238, 4.47 times 10 to the 9th years for this to decay by 1/2. So again, all these isotopes can vary. So we're looking at this question, which of the following radioisotopes has the shortest half-life? So we'll need table N for this, and we'll look up each one of these. So we have 14C, whoops, let's go back. 14C, so it's carbon 14, and here is carbon 14 right there. So that takes 5,715 years for that to be reduced to half. We have hydrogen 3, which is right there, tritium. It's 12.31 years for half of that to decay. 37K, or potassium 37, is right there. It takes 1.23 seconds for that to decay by 1/2. And 32P, which is right there, takes 14.28 days. So the shortest half-life should be the smallest amount of time. So we should have C for that answer. To do the calculations, you need some basic pieces of information. You need the initial amount, the final amount, the half-life, periods, and total time. The question might give you a combination of these. Some questions may not even need some of these filled in. So if they ask you about the fraction remaining, your initial amount should be 1. All right, so make sure you get a note on that. The half-life, sometimes we can find that on table N. The periods, meaning how many times it undergoes decay, that's the total time divided by the half-life. So they could ask you a bunch of these different things. They might give you the initial, the final, and the periods and total amount. They might ask you for the half-life in that case. So they wouldn't tell you which one of these nuclides it would be. If they ever give you a nuclide, always look up its half-life, because that's probably where you're going to get the half-life from anyway. So let's go through some calculations. Make sure you have your calculator ready. A radioactive element has a half-life of 2 days. Which fraction which fraction represents the amount of an original sample of this element remaining after 6 days? So, the radioactive element has a half-life of 2 days, so the half-life is 2 days. Which fraction? So if they ask about fraction, the initial amount should be 1. Represents the amount of an original sample, so this is your unknown, and they word it funny. They should say like the represents the amount of the original sample remaining. Sometimes they don't. They kind of put the remaining right there. So just don't miss that. So don't assume that they want the initial amount or the original amount. They want the time remaining, which is right there. And then it says after 6 days. So 6 days will be our total time. So right now we're missing the number of periods. So to figure out the periods, we do the total time, which is 6 days, divided by the half-life, which is 2 days. So that's 3 periods. So we're going to cut this initial amount 3 times, or cut it in half by 3 times. So we'll take the initial amount, which is 1, because they wanted the fraction remaining. So we always start with 1. And let's cut that in half. So it should be 1/2. So that's 1 period. Cut in half again, so that's a 4th. And then again should be an 1/8. So we have 1, 2, 3 periods that this has undergone. So the final amount is 1/8. So really, each one of these times it takes is 2 days. So 2, 2, and 2. The total time should be a total of 6 days. That's what we have here. So 1/8 is their amount remaining, or the fraction remaining. The next question, what mass of a 60-gram sample of 16N will remain unchanged after 28 seconds? So we have, let's see, 60-gram sample, that's our original amount. And it wants to know what mass will remain, so that's our unknown amount. And unchanged after 28.8 seconds, so that's our total time, 28.8 seconds. So we don't have the half-life or the periods, but they did tell us it was 16, or nitrogen 16. So let's look up nitrogen 16, and it's right there. So we'll use the 7.13 seconds that we've taken from table N, and now we have to figure out the number of periods. So we have 28.8, the total time, divided by the half-life, which is 7.13, and that's roughly about 4 periods. Now the period should be a whole number, so if they're not exactly a whole number, round it to the whole number. So it takes 4 periods for this to decay. So let's start with the initial amount, 60 grams, and let's cut it in half 4 times. So let's cut it in half once, so that's 30 grams, 15, 7.5 after that, and 3.75. So let's make sure we have 1, 2, 3, and 4. Good, so the final amount should be 3.75 grams. Alright, and another question. What is the total number of grams of a 32-gram sample of 32P remaining after 71.5 days of decay? So the total number of grams remaining, so that's our unknown, our X, of a 32-gram sample, that's our initial, remaining after 71.5 days of decay. And they tell us it's 32P, so let's go ahead and find that. 14.28, and that's in days. So to find the number of periods, divide your total time, which is 71.5, divided by 14.28. And let's see, when we divide that, we should get 5. So we're going to cut that initial amount in half 5 times. So we have 32, cut in half, 16, 8, 4, 2, and 1. So 1, 2, 3, 4, and 5. Good. So it's cut in half 5 times, so because that's the number of periods that we had. Now, most of these were pretty much cookie cutter. They gave us the initial amount, we had to figure out what the final amount was. Sometimes they'll give us the final amount, and we have to figure out what the initial amount is. Or they'll give us all the other pieces of information, and then we have to figure out what the half-life is. Just use this basic formula. You know, it's not technically a formula you put it into, but this basic way of answering some of these questions through. All right, so we will see you guys in class. Take care.